Good morning, grade 11. I know it's a Saturday morning, but anyway, I do have a couple more types of questions that I wanted to go through. So today I wanted to look at how you do a series of connected objects, like a train. And so here you can see this train with many, looks like it's carrying coal there, but anyway, many hundreds of, or perhaps 100 or more than 100 cars. Okay, and let me show you another type of problem. This one is more like, this was from an old quiz. So here's, I think from last semester, a boy pushing 3 boxes across the floor. And then it says, what is the force that box 2 exerts on box 3? All right, so before we do this, one thing that I have not mentioned to you in a while, that some of you have been asking about, because on my course outline I didn't do this yet, it's Newton's third law. So I want to explain Newton's third law. Not that you really need it to do this question, but the third law, okay? Okay, so the third law. What is the third law? Well, the third law is kind of the most famous one when you think about it. For every action, okay? For every action, I'm going to say it like this though, force, because it has to do with forces. There is an equal and opposite reaction. Whoops. Okay. Now, what does that mean? I'm just going to put a little highlight note. These forces occur on different objects. All right, so let me explain that a little bit, and then I will tell you how to do these problems, okay? So what does it mean? Well, basically, it's kind of stating the obvious when you think about it, okay? Like, would it be possible for you to touch an object? Okay, let's say right now I've got like a cup of water in my hand. I know you can't see it, but just imagine that. Is it possible for me to touch the cup, and at the same time it's not true that the cup is also touching me? Well, of course you can't. That's impossible, right? So if you touch something, whatever you touch, it's automatically true that that object is also touching you, okay? Now, if I push up on the cup, it's also true that the cup is pushing down on my hand, okay, if that makes sense to you. Like right now I have my laptop is on the table that I'm using to write my notes and everything. So the table is pushing up on my laptop, right? Well, the laptop though is pushing down on the table. See, all forces come in pairs. That's what this law is saying. All forces occur in action reaction, okay, pairs. Okay, so say for example, here's a table, okay, and here's a object sitting on the table. So here, the free body diagram of, let's say this is a book, okay, the free body diagram of the book looks like this. Okay, here's your book. There's gravity. We've done this many times now. There's a normal force. Okay, and that's it. Now the normal force is the force of the table on the book. Let's call that the action force. Okay, it really doesn't matter which one you call the action force. Now if I draw a free body diagram of the table, okay, well the table is on the floor. So this is kind of an interesting diagram. Let's see how good you are at figuring this out. The table has a force of gravity on it too. But there's actually 2 other forces acting on the table. One of them, oops, let me erase that. One of them is, it of course has its own normal force because it's touching the floor, right? So the floor is exerting a force on the table. right? Upwards, which balances in part the force of gravity. But there's something else. Okay, and I'm going to use actually a different color. I'm going to use the color red for this. So what's also true is that the book is pushing down. Okay, so I'm going to write FB. That is the force of the book pushing down on the table. And actually the normal force from the floor has to balance both of those things, right? And so here's the deal. These two forces, I'll circle them in blue, that's the action. This one is the reaction force. So that is the book on table force, and that is the reaction. So in other words, yes, the table is pushing on the book upwards, but the book is also pushing downwards on the table, and those forces, the amount of contact, if you like, okay, has to be equal. And what the Newton's third law is saying, specifically, the third law is saying that the normal force on the book, this normal force, okay, not this one, this is a separate normal force, this one here, so don't ignore the one that's on the table, ignore that one, that has nothing to do with it. The force of the table on the book, that normal force, has to equal the negative of the force of the book on the table, this one. And that is the third law written mathematically, okay? So there's not really much to do in problems with the third law, but we can prove that it's going to work out that way in free body diagrams. So like you'll see when we do these train problems, that's how it works out, okay? So by the way, another kind of interesting example of action and reaction is with gravity. You don't have to have contact for this to work, action or reaction. So let's say this is Earth, okay, and this is it could be an airplane, it could be whatever, okay. So here's the deal. I'm going to zoom in on this. Is there gravity acting on that object? Well, of course there is, okay, because of Earth's pull of gravity, right? So there's gravity acting on this object. In fact, that's what keeps, like, say, orbiting satellites like the moon in orbit, is gravity. Now, here's the deal, though. It's also true that that satellite is exerting a force of gravity. Okay, you know what? I need to make that pen thinner, so let me do that. It's also true that the Earth is experiencing a force of gravity because, so this is the force of gravity, let's say, because, here, let me do it like this. This is the Earth pulling on the satellite, and this one down here is the satellite pulling on the Earth. But they're both forces of gravity. It's force of attraction between objects that have mass. That's what gravity is, right? Now the thing is that even though the Earth is absolutely huge, okay, it's absolutely huge, it still has the forces between these objects are the same number. So in other words, it works like this. The force of gravity of the Earth on the satellite, okay, must equal the negative of the force of gravity of the satellite on Earth, on the Earth itself, okay? That's the third law. So all forces occur this way, but you see how the two forces are acting on different objects? Like they don't cancel each other out or anything. One of them's on the Earth, the other one's on the satellite, okay? So even though these forces are the same, we know that the acceleration, let's call this the acceleration of the satellite, right? And the acceleration of the Earth would not be the same number, okay? And why wouldn't they be the same? Well, because Newton's second law, here, I'll just write it like this. What about A? Okay, what about the acceleration? Well, the accelerations are not the same because look, the satellite's acceleration, A would equal the force of gravity because of the Earth pulling on it, right? but that's divided by the mass of the satellite, okay? And the mass of the satellite could be 100 kilograms, okay? Really small number. But for the Earth, its acceleration would be the force of gravity that the satellite is pulling on it, which is equal in size to the one from the Earth, okay? But then you divide by the mass of Earth, and this number is huge, okay? This is a huge number because Earth is so big that the acceleration is so tiny that you would never notice it, okay? So if you jump off the side of a building, you're going to accelerate at 9.8. We know that, okay? If you throw a ball, it accelerates at 9.8 meters per second squared. Now the Earth is accelerating upwards too, but that number is infinitesimally small. So small, if we were to work it out, it would take the Earth 1,000,000 years to move like the width of an atom. Well, then no one's going to notice that. Obviously, it's way too small for anyone to notice. So while the forces are equal and opposite, the accelerations are not equal and opposite. And people have a lot of misconceptions about this. Okay, so I just want to give you like a question on a test could be something like this on the third law. Let's say a truck, a large truck is traveling north, okay, and hits a stationary car. Okay, so there's a collision. Now, does the truck exert a force on the car? Absolutely. Okay, so here I'll draw a little picture. So you got this big, that's not good. Here's your big truck, okay, whatever. There's your big truck. It's traveling forward like this, and then it hits this tiny little guy here, your tiny little car. So here comes the truck, and it's going to hit this car. Now this car could have a mass of let's say 1,000 or 500 kilograms. The car could be 10,000 kilograms, okay? Or the truck could be many times more massive, okay? So you get this question, what's true about the force of the truck on the car compared to the force of the car back on the truck, okay? So what does Newton's third law tell us? See, most people would think that the force of impact on the car is way higher than like if the car hitting the truck back. But that's not true. It's a common misconception. So here's the thing. The forces are equal. That's what Newton's third law is telling us, right? The force of the truck, whoops, not the tuck, the truck, okay, on car is equal to the negative of the force of the car on the truck. See, what's going to happen in this collision? The truck will slow down because the car hits it, okay? Like it hit, it's kind of relative, right? That the truck hits the car and the car hits it back, okay? They're both in contact with each other. So that's Newton's third law. But the acceleration is not the same. See, what kills you in a collision is not just the force of impact, it's how much acceleration you get. So if you're in this huge, massive object, okay, like let's say you're the truck driver, you're going to get a very small acceleration as a result of this collision, but the car is going to get a very large acceleration. And we've seen in questions already that if you have a really large acceleration on an elevator, for example, it could actually crush you, okay? So the acceleration of the truck would equal this force of impact, okay, force of the car hitting it, divided by the mass of the truck, right? And the acceleration of the car is equal to this force that the truck is exerting on it, divided by the mass of the car. And because the truck has so much more mass, the forces are the same. These two forces are equal and opposite, right? So the car will accelerate, let's say, north, okay, whatever direction that way is north, the car will accelerate that way. The truck will accelerate actually this way because of the impact, but that's just going to slow down the truck, okay? Whereas the car will speed up in that forward direction, of course, because it's sitting there parked. But what's dangerous is this acceleration. This can be dangerous. this is where the danger is how much acceleration you get. Okay, not necessarily the force directly. The force matters, of course, but like, and the truck is going really slow, then you're going to get maybe a small force of impact, which means a low acceleration for the car. But if the truck is going very fast, you're in big trouble, because if that exceeds 10 Gs, your neck is going to snap, right? Like you'll experience so much, your own inertia will basically kill you there. So it's the acceleration that's dangerous in a collision like this, not the, it's not necessarily the forces. So the forces are the same between these two objects. The common misconception is, oh, like, you know, that truck is going to hit way more force on the car. No, the force is the same. What's not the same is the acceleration. And this, the truck has so much mass, it could have a safer acceleration, to be much lower number, okay? Because its mass is so large. It's this mass of the truck that is larger that keeps the truck driver safer, okay? So it's just, do you get it, right? Like, forces are always equal. So if I am playing hockey and I deliver a body check to the Zdeno Chara, let's say, who's much bigger than I am, why do I fall down and he doesn't fall down? Well, the thing is that I get that force of impact too. Like, as soon as I bump into him, I will feel the force of impact as well, okay? Now, maybe I'm bracing myself because I'm delivering the body check, but I'm still going to get some acceleration. Now, who will get more acceleration? Well, I will, because I'm lighter than him, just because I'm lighter, right? And so when you deliver a body check to a much larger player, they're going to get a smaller acceleration, right? And that's why sometimes the smaller guy falls down and the bigger guy doesn't. Okay, it's because of that. All right, so that's the third law. All right, so anyway, let's talk about how you do connected object problems. Okay, and I've got a sample problem for you, and we might as well just go straight to it. Okay, and I'm going to prove to you that Newton's third law works in this problem, okay, as well. So here's a kid, or whatever. A boy is pushing 3 boxes across the floor, and here, see the 3 boxes here. It says, what force does box 2 exert on box 3? Now, it says the boy, this force here, okay, that he's applying, that force is 300 newtons. Now, some students will say, okay, well, then this must be force of contact here. In this area here must also be 300 newtons. Well, that's not true, okay? And you'll see how we do this when we do the question, okay? Now, there's always 2 steps. So your job is to remember what steps we use in a question like this. The first step is, if the question doesn't tell you what the acceleration is, you have to find the acceleration. Now, the way you do that is you treat, this is the secret to doing these questions, you have to treat all 3 boxes, the whole thing, as one box, okay? Now, you're allowed to do that. They're all touching each other, right? So in other words, can I pretend for a moment the total mass here is 35 kilograms. Let's put a blindfold on you, and I get you to push the system. Would it feel like you were just pushing one box, mass 35 kilograms? And the answer is, of course it would. Okay, so for you, it's just like you're pushing one thing of 35 kilograms. It's all connected anyway, right? So you're allowed thinking of it as one thing. So in order to find A, you draw a free body diagram. Okay, free body diagram of all 3 objects. We're going to combine them and treat them as one. I'm sorry, I'm having a hard time writing this morning. All right, so here, all 3 objects. Now, what does that look like? Well, it says in the question there's no friction, so that's good. But we could put it in if there was. It would be against the motion. There's a normal force, there's gravity. And there's the kid pushing, and because we're grouping them all, treating them as one box, this applied force we know is 300 newtons. Now there's no friction. If there was friction, I would draw it this way, but there isn't any, so let's get rid of that. And we don't have to worry about friction in this problem. So it's going to accelerate like that. So why don't we just cut to it? We don't have to do the vertical forces since there's no friction. I don't care what the normal force is. So let's just look in the x direction. So this is in the x direction, like a horizontal direction. There's only one force. So I'm just going to write it down, 300 newtons. The vertical forces are a separate component, so they do not go in the x direction, right? So now using Newton's second law, ma equals 300. Okay, so ma is 300. Sorry, that was my phone going off. I'm just going to turn off the ringer. Sometimes I forget I'm recording things. Okay, so ma is equal to 300 newtons. And then we know our total mass is, what did I say? 35 kilograms. So 35A equals 300, right? So now divide both sides by 35. Okay, and what's my answer? Well, let me take out a calculator. Okay, so I'm going to go, I'm distracted now with that stupid phone call. Okay, so it's going to be 300 divided by 35 is 8.57 meters per second squared. So I get 8.57 meters per second squared, okay? And that's the acceleration of my system. He's pushing, that's a pretty significant acceleration. He's pushing pretty hard though, 300 newtons is pretty hard on such a small set of boxes there, okay? So that's step one, okay? Now what about step two? Well, step two, we're gonna answer the question, what force does 2 exert on 3? So because, look, I'm gonna circle this, on box 3, that's what it's on, right? So in step two, we're going to answer the question by drawing a free body diagram of box 3, the force that is on that box, right? Okay, so box 3. Now, there's gravity on box 3. There's a normal force on box 3, and I'm just going to zoom in on this. There's one other force here. See, box 2, this box here, is touching box 3 and pushing it forward. So this surface on surface contact here, that's going to push. So box 2 is going to push box 3 forward. So this force here is the force of 2, whoops, is the force of 2 on 3. Okay, and that's going to make box 3 accelerate forward. We know all the boxes are accelerating forward. And we know what rate they're accelerating forward. It's 8.57 meters per second squared. Okay, so look, that is the free body diagram of box 3. So now we just have to find the missing force, right? Well, we know what the acceleration is. So if you like, in step 1, we knew what the force was, but we didn't know the acceleration. Okay? In step 2, we know what the acceleration is because we found it already. Okay, so that number goes over here, but we're wondering what this force is. So the net force, again, we're going to ignore the vertical forces because that component is not relevant in this question because there's no friction. We know the net force is just equal to the force of 2 on 3, right? That's the only unbalanced force on that box. So that's equal to ma. It's the force of 2 on 3. But now this is just a free body diagram of box 3 only. So its mass is 5 kilograms, right? That's the mass up there. So 5A equals the force of 2 on 3. Okay? And then, yeah, so now what we do is we can just put in 8.57. I lost my train of thought there. 8.57 for the acceleration. And we have our answer. Okay, so I'll take out my calculator. 5 times 8.57 equals 42.85. So that's 42.85 newtons equals the force of 2 on 3. See, so definitely not 300. Okay, the kid is pushing with 300 back here, but this box, that box, only gets 42.85 newtons of that. Okay, and that's it. Now, to prove to you that the third law works, what is the force that 3 exerts back on 2? Okay, so let me ask another question with this. Question B. What force does 3 exert on 2. Now we know the answer. We know the answer because of Newton's third law has to be 42.85. Now, but let me prove to you that that's going to be the answer. Okay, so watch. In order to do this, I'm going to draw a free body diagram and I'm going to circle it in red of 1 and 2. Okay, I'm going to group them together because box 3 in a way is pushing both of those things back. Okay, maybe not directly on 1, but indirectly, yes it is. Okay, whereas box 2 is only one thing in front of it, but box 3 there's 2 things behind it, and so I'm going to group them together. Okay, and you're allowed to group them whatever way you like. I can group all 3, just 1, just 2 of them, whatever I want. Okay, it's perfectly legitimate. Okay, so I'm going to draw a free body diagram of 1 and 2, okay, together, combined. And what does that look like? Well, it looks like all the rest. There's gravity. There's a normal force like this. There's the kid pushing because he's pushing box 1 and 2, right? Like he's pushing on 1. So he's pushing with 300 newtons, okay? Now I'm going to put this force in red. But there's box 3 because we excluded it. That's 3 on 2. That's that guy pushing back. Now I got to put the acceleration in. We know this acceleration is 8.57 meters per second squared. We figured that out in step 1. That still hasn't changed, right? All right, so what is this force now? It's that one. Okay, so if we go ahead and work it out, the net force is equal to 300 minus the force of 3 on 2, like this. Okay, and that's AX is 8.57 meters per second squared, so I'm just going to put everything in there now. I'm going to put MA is equal to 300 minus the force of 3 on 2. Okay, so now substituting in the mass, I'm combined 1 and 2, so the mass of my 2 boxes is 30 kilograms. So 30A equals 300. Actually, you know what? Let me fix this. 30 times 8.57, right? That's the mass, 30. So this is 1 and 2, right? Remember, 1 and 2 make 30 kilograms equals 300 minus the force of 3 on 2. Okay, so now there's only one unknown. So I take out my calculator. I go 30 times 8.57 minus 300. I'm just going to do it all in one step. And I get 42.9. Yeah, I get the same number. So I get a negative. I did some rounding, so it's not exactly the same. Oh, forget the negative. I get the force of 3 on 2. I get 42.9. Now, just so you know, newtons, it's in the opposite direction, but we got the same answer that we got in question A, which is equal to the force of 2 on 3. See, and this, therefore, the third law works, right? In other words, what we found is this little red vector of box 3 pushing back on box 2 is the same, okay, as this vector here of box 2 pushing on box 3. And you see Newton's laws, like they work together this way, okay? So we just proved that the third law works. It works on the system of connected objects like this, okay, these action and reaction forces. All right, so one more little note about how you do connected objects. Here I have this picture of a train. What about that? Well, whether you're pushing or pulling a bunch of boxes really doesn't make any difference. You can still think of it as a train, okay? And so I just want to note, I'll just put a little summary here at the bottom, okay, for trains. You always do the 2 steps. Step 1 is to find A by drawing FBD of the whole system, okay? And step 2 is you draw an FBD of a subset of the system to answer the question. And these are really interesting kind of engineering problems too. So here, let me give you another example. Let's say you have a train. Oh, I should have said find A here. Okay. Let's say you have a train that has like the locomotive has a mass of, let's make it 30 tons to 30,000 kilograms. Okay, trains are big. And let's say each car has a mass of 10 tons of coal, let's say. And let's say there are 100 cars in total. And let me ask you a question like this. I'll give you the first step so that you don't have to do it. So I'll tell you that the acceleration of the train is 2 meters per second squared. Okay. And trains usually have a small acceleration, probably less than that normally. Okay. But all right, so you have an acceleration of 2 meters per second squared. And here's my question for you. What is the force that car 33 exerts on car 34? And we'll number the cars in order after the locomotive, right? So let's say you have your I'm sorry, I'm not good at drawing trains. I'm not good at drawing anything really, but let's say this is your locomotive here at the front, my little weird looking train. I don't know why I drew that thing at the front. And then you have like car 1, car 2, car 3. I'm not going to draw 100 cars. So 1, 2, 3, and this whole thing is accelerating at 2 meters per second squared, right? And there's no friction. It's rolling system, so usually with wheels and stuff you mitigate the friction, so that's it. Okay, so anyway, there's your train. I'm sorry it's a terrible diagram, but I mean that's my style. So okay, so you have this thing. What force does car 33 exert on 34? Well, the thing is what you have, the secret to getting this question. Step 2, we're going to go straight to step 2 because we've got acceleration, so step 1 is given. So you don't have to do step 1. So now this becomes a one-step problem. Okay, so let's go straight to step 2. You're not just going to draw a diagram of car 34. Okay, if you do that, then what's happening is you're going to have two forces on car 34. One of 33 pulling it forward, which is the one we want, but then this 35 is pulling it back. And so we don't know what that is, so it's going to be two unknowns. But we're not going to do that. What we're going to do is we're going to realize that car 33 is pulling all cars behind it. So how many cars are behind car 33? Well, if we number the cars from 1 to 33, right? So that's 33 cars at first. 100 minus 33 is 67 cars. So there's 67 cars left. So that is 67 cars in total. Okay. Okay, 67 cars in total. Sorry, a little distracted there. And what happens is you go like this. You're pulling 67 cars, right? So each one has a mass of 10,000 kilograms, right? So therefore, the free body diagram, whoops, FBD of car, not just 34, but 34 to 100, okay? Cars 34 to 100, that is 67 cars in total. What does it look like? Well, when you group them all together, okay, so let's say we group a whole bunch of cars together, that's only, see, look, it's going to go like this. There's gravity. there's a normal force. And then there's car 33, the force of car 33, that is pulling all 67 of the cars behind it, right? Not just one car, it's pulling all the cars behind it when you think about it. Okay, and it's going to accelerate, and we already know that that's 2 meters per second squared of acceleration because it was given. All right, so now this becomes a really easy problem, right? All you got to do is do the horizontal forces. F net equals only one force, the one that we're looking for, and that has to equal ma according to Newton's second law, right? So you just do it like that. And now what's our mass though? Well, our mass is 67 cars, so it's going to be 67 times 10,000. It's not just one car, right? So 67 times 10,000, what is that, 670,000 times 10,000. Oh, 67, sorry, I made a mistake, times 10,000. 670,000, yeah, of course. Okay, so 670,000 kilograms. So I'm going to go 670,000 times 2 is our answer. Okay, and so the answer is just times 2. 1,340,000. I'm just going to do it in scientific notation. F33 equals 1.34 times 10 to the 6 newtons. Okay, now is that a big number? Well, of course. The train is huge, okay? And a kind of engineering question for you, you know, how thick does the steel have to be that connects these trains together? Well, very thick, because steel has a certain tensile strength, it's called. So in order for it to withstand, like let's say I attach my trains with just like my cars with like a piece of rope, okay? Well, a piece of rope is not going to be able to withstand that kind of tremendous force. So you're going to need something that can take it, right? And so if you look at the sort of ties that tie the train together, they're very sort of thick industrial steel. It has to be that way because that is a tremendous amount of force. And while the train is accelerating and decelerating, those ties have to hold together. They can't break off, right? So, you know, you're going to need very thick cabling or steel to withstand that kind of force. All right, so that, guys, is how you do train problems. Now, I only have a couple other, like I have like to do like the two-dimensional type of problems. That'll be a lot quicker than this one, but that is how you do connected objects, and that is Newton's third law. All right, guys, I hope you're having a good weekend, and enjoy the rest of it.